Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 8, 2026, just 1 week ago. It introduces a systematic modernization of vision transformer backbones by adopting architectural refinements from large language models, achieving over 84% top 1 accuracy on ImageNet 1K. The paper is titled ViT-5, Vision Transformers for the Mid-2020s. And, as we'll see later, the results suggest that standard vision models still have a lot of untapped potential. So Figure 1 details the architectural upgrades that define ViT-5. On the left, the input stage now includes register tokens, shown as hatched boxes, which help process background information without distracting the main patch tokens. The right side expands the transformer block, revealing components adapted from modern language models. For instance, it uses RMS norm, applies rotary positional embeddings to the attention mechanism, and incorporates layer scale, which is crucial for stabilizing training in deeper networks. Well, while layer scale is beneficial, Table 2 reveals a surprising conflict when we try to combine it with SWI-GLUE MLPs, which are standard in modern language models. If we look at the third row where both components are used, performance actually degrades to 83.7% accuracy. The authors call this the overgating issue, because both mechanisms filter information channel-wise, leading to excessive sparsity when combined. As a result, the bottom row shows the winning strategy for ViT-5, keeping layer scale but sticking to standard MLPs, which achieves the best result of roughly 84.2%. Moving on, Table 1 investigates whether the post-normalization standard in large language models offers any advantage over layer scale. It compares top 1 accuracy across 3 model sizes: small, base, and large. The results show that both methods yield nearly identical performance. For example, the base models differ by only 0.01%. Because the outcomes are so similar, the authors stick with layer scale for ViT-5, citing its flexibility and lower overhead. Alright, with the normalization fixed, Figure 2 turns to spatial encoding. This comparison highlights a phenomenon the authors call undesired invariance. Panel A displays the original photo, while Panel B shows a version where the image patches are flipped. Surprisingly, if the network relies solely on rotary positional embeddings, it treats these two distinct inputs as mathematically equivalent. To ensure the model can tell them apart and maintain strong spatial reasoning, ViT-5 explicitly adds absolute positional embeddings back into the architecture. So, Figure 3 demonstrates the practical payoff of this design, specifically for handling dynamic resolutions. The charts track validation accuracy for small, base, and large models, which were all trained at 224 but tested across a wide spectrum of sizes. Notice the gray curve for DIT3. It relies strictly on absolute embeddings, and its performance crashes as soon as the resolution scales up. In contrast, the blue line shows that ViT-5 maintains high accuracy even at much larger input sizes, confirming that the mixed positional encoding is far more robust. Okay, with the architecture finalized, Table 5 presents the main ImageNet classification results. It compares ViT-5 against ConvNeXt and DEIT3 across varied model sizes and input resolutions. Looking at the base models with 224 inputs, ViT-5 achieves 84.2% accuracy, clearly surpassing the 83.8% of DEIT3. The gains scale up effectively too. At the bottom, the large model with 384 inputs hits 86%. This confirms that these systematic refinements yield a state-of-the-art plain vision transformer. Well, having established that the full model works well, Table 10 breaks down exactly where those gains come from. It runs an ablation study, starting with the complete ViT-5 at the bottom, and then removing or swapping out individual components one by one to measure the impact. Notice the row for swapping GLU to SWI-GLU. This causes the largest average drop of 0.42%, confirming the overgating issue we discussed earlier. Removing layer scale also hits hard, dropping accuracy by nearly 0.3%. Crucially, the negative values in the delta column show that every single design choice contributes positively to the final success. Wrapping up, 2 takeaways stand out. Vision transformers remain highly competitive when modernized, with current techniques like rotary positional embeddings, proving that the architecture itself is far from outdated. At the same time, the research shows that blindly copying language model designs can fail, meaning specific adaptations like avoiding overgating are crucial for success. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.